Last time we finally said what a matrix is. A coordinate description of a linear map after choosing bases. Today we define matrix addition, scalar multiplication, and matrix multiplication. The last one is not just row-column ritual. It is composition of linear maps. The key formula was this: output coordinates equal the matrix of the map times input coordinates. So matrices are how linear maps look after coordinates enter the room and make everything computable. Because apparently abstraction needed receipts. First, matrix addition. Two matrices can be added only when they have the same shape. If A has entries Aij and B has entries Bij, then A plus B has entries Aij plus Bij. For example, add each entry to the entry sitting in the same position. Different shapes cannot be added. This is not discrimination. This is basic compatibility, a concept humans also keep rediscovering badly. Why is entrywise addition the right definition? Because it matches addition of linear maps. If S and T are linear maps from V to W, their sum is defined pointwise. After choosing the same bases, the matrix of S plus T is the matrix of S plus the matrix of T. So entrywise matrix addition is not random arithmetic. It is linear map addition wearing coordinate clothing. Next, scalar multiplication. To multiply a matrix by a scalar, multiply every entry by that scalar. For example, multiplying by 3 triples every entry. Stunningly, no hidden subplot. This matches scalar multiplication of linear maps. The matrix of lambda T is lambda times the matrix of T. Now for the main event, matrix multiplication. Suppose T maps U to V and S maps V to W. Then S composed with T maps U to W. Matrix multiplication is defined so that the matrix of the composition equals the matrix of S times the matrix of T. Notice the order. S after T becomes matrix S times matrix T. Composition already chose the order. Matrix multiplication is merely following orders. For once. This definition immediately explains the shape rule. Let A be M by N. Think of A as sending N coordinates to M coordinates. Let B be P by M. Think of B as sending M coordinates to P coordinates. Then BA sends N coordinates to P coordinates, so BA is P by N. The middle M must match. If it does not, the composition does not make sense. And neither does the product. Even algebra has boundaries. Now let us derive how to multiply the matrices. But slowly enough that the formula does not fall from the ceiling like a badly installed chandelier. Take Ej, the standard coordinate vector whose only non-zero entry is a 1 in position j. Multiplying A by Ej selects column j of A. We call that column Aj. This is already the hidden reason columns matter. The standard basis vectors ask a matrix what its columns are, like tiny coordinate inspectors. Now apply B after A. The product BA applied to EJ means B applied to AEJ. But AEJ is column J of A, which we called AJ. Therefore column J of BA is B times column J of A. So BA is obtained by applying B to every column of A. This is composition, not numerology with brackets. Now we turn that column rule into the entry formula. Focus on column J of A. Its entries are A1J, A2J, down to AMJ. To compute B times that column, use the usual matrix vector rule. One row of B dotted with that column. Now look specifically at row I of B. Row I of B dotted with column J of A gives this expression. Multiply matching entries. BI1 times A1J. plus bi2 times a2j, and keep going until bim times amj. Because this came from B times column J of A, it is entry I of column J of BA. Now we can write the official entry formula. So entry ij of BA equals bi1a1j plus bi2a2j, plus all the way to bimamj. In summation notation, entry ij is the sum from k equals 1 to m of bik times akj. That is the matrix multiplication formula. It is not an arbitrary recipe. It is composition, then columns, then row. Column. Let us compute one example before the formula starts looking like a decorative curse. B is 2 by 3, and A is 3 by 2, so BA is 2 by 2. Each entry comes from one row of B dotted with one column of A. After doing the arithmetic, we get the matrix with entries 2, -1, 10, and 4. Now let us summarize the basic algebraic properties. Matrix addition is commutative and associative. Matrix multiplication is associative because composition of linear maps is associative. Multiplication distributes over addition from both sides. Scalar multiplication also distributes over matrix addition. It would be alarming if it did not. And yet here we are checking. But now the warning label, matrix multiplication is not commutative. Here are two square matrices A and B. Multiplying AB gives one matrix. Multiplying BA gives a different matrix. So AB is not equal to BA. Order matters. This is composition again. Doing one operation and then another is not usually the same as reversing them. This is the first rule of matrix multiplication club. Do not casually swap the order, unless you enjoy manufacturing wrong answers with confidence. Let us summarize before the matrices unionize and demand better notation. Matrix addition is entrywise, and it represents addition of linear maps. Scalar multiplication is entrywise, and it represents scaling a linear map. Matrix multiplication represents composition of linear maps, which is why the order matters. Addition behaves politely. Multiplication is associative and distributive, but not commutative. Civilization survives. Barely.